there's a couple of things that I want to make sure I clear up. First is, with propagating fields in the phasor domain, I think I put this down that H is equal to 1 over eta AP cross E. Here, the electric field and the magnetic field are assumed to be in the phasor domain. Eta is just the intrinsic impedance of the media, and AP is a unit vector in the direction of propagation. Did I cover this last time or not? Not yet. Okay. So here, AP is a unit vector in direction of propagation. Right. Likewise, the E field is given as minus eta times AP, unit vector in the direction of propagation, crossed into the H field. Now I'm gonna show you, these are much easier to do than curls. Like before, if you have E and you wanted H, you'd take curl of E and set it equal to minus j omega mu H to get the H field. Well, doing a curl equation takes a little time. It's much easier to do this. Y'all follow me, class? So now I'm gonna show you what these things mean in terms of practical things. So if I give you an E field, let's start with the E field. E field equal to, and I'm just gonna put E naught, E to the minus J beta Z in the AX direction. That is the field that we were using before it was lossless, right? So if I wanted to take that field, I'm going to examine it and locate the direction of propagation. How can you tell the direction of propagation? Anyone?
Negative as Z.
Whatever the coefficient is, I mean, whatever the variation up here in the exponential, that's the direction it's going, either positive or negative. If there's a minus j beta z, it's going in the positive z direction. If it's a plus j beta z, minus z direction. Do y'all follow me on that? So I can say that the unit vector in the direction of the propagation here is just az. Then after that, I want to get the H field. Now this is rudimentary. It's very simple to do. But I want to start here. So the H field, let's say it's in air. So air has eta equal to eta naught, or equal to 120 pi ohms. So the H field itself would be equal to 1 over eta naught AZ, and here I'm just copying the definition right here, and it's going to be crossed into the E field. Well, this is the E field, so it'll be crossed into E naught, E to the minus J beta Z in the AX direction. Y'all follow me? I'm trying to be as clear as I can, make it as simple as possible for the first time around. Now, when you do this, you'll see the cross product. Really, the magnitude is just E naught over, now try to not go too far down here. The magnitude will just be E naught over eta naught. That's the magnitude of the H field. Then, I have E to the minus J beta Z. So I know that it's the same phase as the E field. There's no phase difference. Then I have AZ crossed AX. What is that? It's going to be AY, right? And in case you don't know these things, or haven't thought about them in a while, when you have X cross Y cross Z, in this direction they're all positive. AX cross AY is AZ, AY cross AZ is AX, and so forth. Now, if you go in the other direction, this way, these are all minus values. So if you create Z cross Y, it's minus AX. You all remember this stuff? I'm just making sure that I'm clear about this. So I have AZ cross AX or AY. Now that's simple enough. Do you all agree? Immediately, if you know how to get the direction of propagation, which you get from the exponential coefficients, and you remember these simple laws or simple relationships, you have no problems doing that. If you have the E field and it's a plane wave, you have the H field necessarily. Now one other thing I'm going to mention, without going into too much detail, quite yet, because we'll do this with power, is the E field and the H field are orthogonal to each other for any propagating wave. If you have a propagating E field, you necessarily have a propagating H field, and it is both are perpendicular to each other in the direction of propagation. So I want to be clear about this. If this is the vector E field in this direction, and it's propagating, the wave's propagating that way, well, the H field will be in this direction. And it will be propagating that way. And these two are linked by those equations, they can't be separated. One, if you have an H field that's propagating, you have an E field that's propagating, that's the relationship. Y'all follow me on this, guys? One other thing, I'll just say too, if you think about this, eta naught, or eta in general, is just the relationship between magnitude of the E field that's propagating and the magnitude of the H field. And that's always true for propagation, the way it's propagated. Now, I want to do one other thing here, make sure I'm clear about this. This is a real simple problem, but I think I gave you a problem. Unfortunately, I don't have it up here. I think I gave you problem 6, 7. Can anybody confirm that? Yeah. I did give you it? Okay. Now, if you look at this one, it's a little tricky, and now I'm going to go to the next step and make sure you're clear on this. Can you read that to me?
I don't have my laptop there.
6.7?
Yeah.
Suppose that E of x, y, and t is equal to 5 cosine of pi times 10 to the 6 t.
All right, I'm going to just put omega t, and I'm going to put omega is 5 times 10 to the 6 t. 5 times 10 to the 6.
Pi times 10 to the 6.
Oh, pi, well, this whole thing times pi. Okay. Omega t minus, go ahead.
3x plus 2y.
A, z.
Yes.
It would be volts per meter. Now I've got a field quantity I put in the time domain, and now I don't have just one spatial variation, I have both x and y. Do y'all follow me on this, class? Now it becomes a little more tricky, so I want to make sure I show you how to do this. The first thing I'm going to do is put this into the phasor domain. To put it into the phasor domain, the magnitude stays the same. You're going to suppress the omega t, and the only thing you retain is this. So it becomes e to the minus j, and then it would be 3x minus 2y, az. I'm going to make a comment. I know that this wave, in the direction I want it to travel, has the form of the E field equals sum E naught times cosine of omega t minus some beta, and then you can call this z prime here. Now that vector direction, the thing that's multiplying beta, will give you the unit vector, and I'm going to explain this in a little more detail, so pay attention to this. Now, here, I made sure I had minus j beta, really minus j, this would be beta z multiplied out, or beta z prime. The reason I did this is, now I can break out both the magnitude of beta and the relative strengths of the x and y weights, and I'll show you what I mean by this. So I have this 3x, and I have minus 3x, let me do this, 3x minus 2y, and that's really equal to beta times I'll call it z prime. That's going to be a vector in the direction of propagation, but it's going to have a unit magnitude, and I'll explain this in a second. So to get beta, right here, you're going to take the square root of, this is really what I'm showing you here, is beta x, beta sub x times x, plus beta sub y times y. You'll follow me on this? There's a beta sub x, this has to do with the wave number in the x direction. Beta sub y would be the wave number in the y direction. Now, it'll become a little easier in a second. To get the actual value of beta, that's equal to beta x squared plus beta y squared. Well, that would be equal to the square root of 3 squared plus 2 squared. And that's going to be equal to, that's 9 and 4 square root of 13. Y'all follow me, class? Please, just watch this. It'll make a lot of sense in a second. So I come back to this E field, and now I'm going to write the E field as 5. And it's going to be E to the minus j, and now I'm factoring out what the true beta is. So I'm going to take the square root of 13 out in front. All right? Now what's left is going to be 3x over the square root of 13 minus 2y over the square root of 13. And it's in the AZ direction. Y'all follow me on this, guys? Why did I do that? Well, you see these coefficients right here? Those give you the virtual, you might say, the weight of that term, the x term and y term, how much of that wave is propagating in x and y. Do y'all follow me? Now, if you want a unit vector in the direction of propagation, unit vector means magnitude of 1, right? Just take a look at this for a second. If I take just those quantities, I got the beta outside of there, and I square them, if I take this squared plus that squared, square root, you get 3 over 13 squared, that's 9 over 13, right? Square root of 13. And then it would be plus 4 over the square, or 4 over 13, which is 13 over 13 is 1. The coefficients here have a magnitude of 1. When you actually look at it. So what am I getting at right here? So now, if I plot this, if this is x and this is y, I can see that the relative x component, the weight on the x is 3 over 13. So I'm just going to say that's 3 over square root of 13, actually. And for the y, it's minus 2 over square root of 13. Now, if you look at that, this right here would be a unit vector in the direction of propagation. And what you really do at this point is say that unit vector, there's probably better ways to do it, but Dr. Whitman's book uses a curl. I don't like doing a curl if I don't need to. What he'll do is take this and he'll say the curl of E right there will be equal to minus j omega mu h. Then when he has h, what he'll do is say curl of, or he'll take E cross h over the magnitude of E cross h is a unit vector in the direction of propagation. That's too much work. The way I like doing it is this way, and I'll show you what he does. But forget this unit vector; it's simply equal to 3 over the square root of 13 ax minus 2 over the square root of 13 ay. Now, can you appreciate what's going on here? These two, if you square those quantities, and I could get into this deeper. Usually, this term right here that I have there is usually k vector or b vector. It's an actual vector dotted in to ax times x plus b or plus y times ay. And you don't need to do that if you just see this right here. Now, does this make sense to you for what I've done? So I'm just going to talk about this. So if I wanted this unit vector, that's it right there. I've got the unit vector. So if I wanted to get, that's the E field. That was the E field in the time domain. This is the E field written in a form that's useful to get the unit vector. Do you all follow me? Now, if I wanted to get the H field, what would I do? Well, I'd go up here and I'd say 1 over eta, assume it's free space. Then I'd take that unit vector and I'd have to cross it into that E field. Do you all follow me, class? Now, I'll ask you this, and you think about it for a second. So that's Wentworth's, by the way, I don't have the solutions in front of me for this one. What does he ask for? Find the direction of propagation. I just did. Find H. H, the way we're going to find H is through basically that. 1 over eta, unit vector, in the direction of propagation, crossing the E field. That's what it is. How many tried that problem, by the way? 1, 2. It should have caused you some concern, because he did it by taking, I believe he got curl of E to get H, equal to minus j omega H. All right, curl of E is a pain sometimes. After that, he said that, well, a unit vector in the direction of propagation is going to be E cross H over magnitude of E cross H. That's a lot more work than what I'm showing you right here. The reason you can do this is because we're not there yet, but E cross H is going to be something called a Poynting vector. It's the direction of propagation. All right, but it's not a unit vector. To make it a unit vector, you have to divide that by the magnitude of E cross H. Then you have a unit vector. Okay. One more thing, so I make sure everybody's got this. We'll keep on going. One second. I want to give you one more problem related to this. This usually causes people some angst. gave you this. And I'll put up the relationships, so I know that H is equal to one over eta, unit vector in direction of propagation across E, and E is equal to minus eta, unit vector in the direction of propagation crossed into H. Those are the two. So now I'm gonna give you another problem, and you just talk to me about how you'd solve it. Here, I'm giving you an E field, 10 times cosine of 500t, these are just random numbers, minus 5x plus 4y in the AZ direction, okay? That's the E field. And assume it's volts per meter. How do I go ahead and get a unit vector in the direction of propagation? That's the first thing. Remember what I did? Any suggestions at all from anyone?
Put it in phasor form.
Yeah, and what are you gonna do then? You're absolutely right. The 10 stays there. What do I do next? You make a T, or that 500T, suppressive, right? Y'all follow me? We'll assume it's in free space too, so we'll say that beta is just beta naught, or 120 pi of it. Then I do what? E to the minus j, right? And then it's gonna be what? Right, 5x minus 4y. Remember, you want a minus sign in front of it, right? Because this is gonna be the magnitude of B times the actual components in the x and the y direction, the fractions of it. So then, what's my next step? You're right about this. E to the minus j. Well, what do I need? I need B, right? Beta. That's the square root of, this is Bx, this is By, so I can say that the actual beta for this problem would be 5 squared plus 4 squared square root. You all follow me on this? All right, so that's what, 25 and 16.
Where is it?
Pardon me?
Use a, oh, sorry,
41.
41.
41, right? Equals square root of 41, right? Now, I can say that's the square root of 41. We really don't need to go this far. And then it's going to be 5 over square root of 41 times x minus 4 over square root of 41 times y. Y'all with me? So what is the unit vector? That unit vector in the direction of propagation is actually 5 over the square root of 41, whatever that is, ax, minus 4 over the square root of 41, ay. Okay? Now these got values, but this value squared and this value squared, square root of is 1, guaranteed. Are everybody following me on that? Yeah.
Can you explain what you factored out the -1, like in the exponent?
Remember, in general, if you have E naught, e to the minus j beta z, that's a wave traveling the plus z direction, right? Well, to get the unit vector, I need the direction it's traveling, so I make sure I have a minus j there, and then I pull out the beta terms, alright, that way. But anyway, you can get the fractional values of these. Y'all follow me on this? And that is a unit vector. Now that unit vector is what you use to go ahead and get the H field from that equation. I'm not gonna go ahead and do it, but I wanna make it absolutely clear.
Would you need to pull out the J on the say you get the negative square root of 41?
Yes.
Yeah.
It's on me, sorry.
No, you're good.
No,
I was just wondering where it went.
It went, it vanished magically because I didn't put it there. But that's all. I mean, you follow me, guys? The way Wentworth's book does it, one more time, here's what he does. First, it's based on things ahead that we haven't covered. But he says E cross H is actually the pointing vector. It's a vector that shows the power in watts per meter squared in the direction of propagation. He takes this and divides it by magnitude of E cross H, and then he gets that over P magnitude, which is a unit vector in the direction of propagation. But to get the H field, you have to do the curl of E, which is a pain sometimes. And so I don't like doing curls unless I have to do them. I prefer just doing it this way. Okay, enough said about that. Next. That was one of the problems I gave you I thought I'd hear about. All right, now we're going to get into the sections that come, the next couple of sections are propagation of lossless and low loss dielectrics. So lossless media, it's just something where the conductivity is zero, so you don't worry about any attenuation at all. And this is really not hard. It's just being aware of this. So, if you have any kind of media and you see that sigma is zero, that's lossless. There's no losses. If you don't have a value of sigma, or there's an equivalent thing, you'll see that it's effectively a type of sigma for low loss dielectrics. You don't have any power loss. That means when you look at gamma, which is alpha plus J beta, that's equal to square root of J omega mu times sigma plus J omega epsilon, right? That's fundamental. But if you have sigma zero, then I have J omega mu times J omega epsilon, that's equal to what? Just J omega square root of mu epsilon. Y'all follow me on this, guys? Right, if sigma is zero, then it's J omega times J omega squared root of that is J omega. And then you have square root of mu epsilon, right? Now, mu epsilon is actually equal to, I can say this is J omega square root of mu naught epsilon naught times square root of mu relative epsilon relative. You all agree with that? What is that? Well, that's J omega. This is what? Square root of mu naught epsilon naught? How about 1 over the square root of mu naught epsilon? What is that? Speed of light, that's right. C is equal to 1 over the square root of mu naught epsilon naught. And that's about 3 times 10 to the 8. 10 to the 8 meters per second. If you're an electrical engineer, electrical and computer engineer, that's something that's got to be known without question. You come down here, so that's really omega over C, and that's times the square root of mu relative epsilon relative. And that is simply going to be just J beta. Alpha is going to be 0, and that means beta is simply equal to omega over C square root of mu relative epsilon relative. And that's for a lossless material, or a lossless region space. Now, if that's beta, how do you get phase velocity? I like to go through it this way. We got beta from the definition, right? From the fundamental definition. What's phase velocity always?
Omega over beta.
That's right, omega over beta. That's going to be great. So if I take omega over beta, what do you see happening? It becomes C over the square root of mu relative epsilon relative. You all follow me on that, guys? Can you all see in the back of the room there? Everybody? Are you good with this? Can you see it okay? You can't see it? You can't see it. Okay. Now, the reason I'm putting it this way is because you can see C is the speed of light. So, that's as fast as it goes. Mu relative and epsilon relative in the medium will be 1 or greater than 1. It would only slow it down. Y'all follow me? And that's the thing you have to be aware of. And there's something, I almost don't want to mention this, but I think I should. Now, the true speed of a photon, regardless of the media, is always the same. It is C. Doesn't matter. However, when you get into materials that are not free space, the actual photon path gets deflected slightly. And that deflection accounts for the reduction in velocity in the direction it's going. Just remember that. Now, it's well beyond the scope of this class to get into that kind of physics, but it's true nevertheless, and you should be aware of it. So that's the phase velocity, that's beta. One last thing, if it's lossless, if I talk about eta, technically it's square root of J omega mu over sigma plus J omega epsilon. Do you all remember that? All right, if sigma is 0, what does this become? That's right, square root of mu over epsilon, or you can say that's simply square root of mu naught over epsilon naught times the square root of mu relative over epsilon relative. All right, what is the square root of mu naught over epsilon naught? The intrinsic impedance of the media, right? You remember that? So this is equal to just eta naught times square root of mu relative over epsilon relative. And again, eta naught is just 120 pi, and that is the ratio of the magnitude of E over the magnitude of H for propagating waves in that medium. Okay? Alright, the next part, now that part, it's fairly easy. You just have to realize that if you have a mu relative, epsilon relative, and sigma 0, there's no loss. The velocity scales down as a square root of epsilon relative and mu relative. The intrinsic impedance actually goes down by square root of epsilon relative, but it increases with square root of mu relative, if you take a look at that. And the phase velocity, it just slows it down, basically. But that's the thing you need to worry about. So now, the next thing is, when we talk about dielectrics that aren't perfect dielectrics, they're low-loss dielectrics. So this one is the next section of the book. And let me explain something about dielectrics, or I like to call them insulators sometimes. I mean, why do we put, say, mica in between the two plates of a capacitor, little mica capacitor? Why do we have these insulating coatings on coax cable or two-wire pair? Anybody? There's two things that happen. It prevents shorting. That's the first thing. It holds it as a constant cross section. It doesn't short out, right? That's the first thing. The second thing is this. The dielectric, or the insulator, allows you to put a larger voltage across those 2 points before it breaks down. When I talk about breakdown, think of lightning. That's the atmosphere breaking down electrically. All right. So when you put mica or any other dielectric in between the plates of a capacitor, you increase the amount of voltage you can have across those plates. Increase the electric field strength. Do you know what the breakdown strength is for air of the electric field? How many volts per meter of electric field would I need here before I got an arc? You all know what I'm talking about, right? Spark. Anybody? I mention this all the time because most people don't know this, but you should if you're an engineer, especially in the field. About 3 million volts per meter in this room, right? Now, 3 million volts per meter sounds like a lot, but when you scale that down to volts per micron, or volts per, say, millimeter, then that's 30,000, 3,000, and stuff like that. That's very attainable in modern electronic circuitry. As a matter of fact, so you have to understand that you can't use air as the dielectric most of the time. Now, if you talk about the breakdown strength for, and I think he has some of this in the back of his book, I'm gonna actually take a look. For things like mica and stuff, they're more than an order of magnitude, up to 2 orders of magnitude larger fields. That means they can hold a lot more energy, and they can also have a lot of standoff breakdown strength. So let me just try to show you if he has it. If you guys find it before me, let me know, because this book of mine's falling apart, which is normal for a well-worn book. He usually has it in his back, but it may have fallen out of mine. Do you see anything with breakdown strength? No, maybe it's here. Hold on.
It's on page 625 under appendix E.
I see it. So air is about 3 times 10 to the 6. Then if you look at glass, 30 times 10 to the 6, mica, 200 times 10 to the 6. So it scales up quite a bit for mica and some of the others. With exotic materials, it can get much higher than that, I believe. But it is frequency dependent. I wanted to make sure I've at least made you aware of this, the dielectrics, what we're talking about. Now, with a dielectric, no real conduction current moves from one plate to the other. And I mean by this, if you could somehow, think of this as a thought experiment. If I could spray paint an electron blue, it would never move from that plate to the other plate. That electron can't move through there. But what it can do is induce charge in the other plate. So if I have a lot of positive charge on this plate, it induces negative charge on this plate. And in doing so, it causes the dipoles of the dielectric to flip back and forth. Now you have microwaves. You know, microwave heating simply takes the water molecule and flips it around and causes thermal energy, right? It dissipates energy that way. In a dielectric, you'll get these things. They're not going to move. they're in place, but they're gonna wiggle back and forth and cause a frictional loss and heat it. That's a loss, but it's not real current. It's not, you know, when you talk about J or sigma E current, it means actually if you could spray paint that electron, it's gonna flow through the lattice and go to the other spot where it's trying to get to. You all follow me? But when you have a dielectric with dielectric current losses, the dipoles just wiggle and heat up, and that is the reason for the loss. So here's how we do it, and I'm not gonna spend a whole lot of time on this. But normally, when you have curl of H, so this is gonna be low loss dielectrics. Normally you have curl of H is equal to J, right, plus the partial of V with respect to T. Now J in this equation, that's real current flowing, current density. It means charge is moving a significant distance. This is called displacement current, right? Partial of V with respect to T. Here, nothing's really moving. So, if I take this and I put it into the phasor domain, J is sigma E, right? And I would put this one, I would put plus J omega, because it's a time derivative, then D is epsilon E, I get this. Or I could say, if I want to, I could factor out J omega epsilon, and this is the way actually it's usually shown. And then I would have 1, and I'd have minus J over sigma over omega epsilon times E. And I'll explain what I did here. Yeah. So if I divide this by J omega epsilon, I pull out J omega epsilon, that means I have to divide every term there by J omega epsilon. J omega epsilon divided to J omega epsilon is 1. This term is the loss term associated with the loss. I divide that by J omega epsilon. Well, 1 over J is minus J over sigma omega epsilon. Do y'all follow me on this? Now, we don't have a sigma that allows conduction. So the way they actually write this is this. They say we're going to have a J omega, and it's going to be epsilon complex times E. And here, epsilon complex is going to be rendered as J omega, and it's epsilon prime minus J epsilon double prime times E. Try to appreciate what we're doing is, we're trying to distinguish between actual current loss, which is the sigma, the real sigma. So we don't have that, but we have something that looks just like that. We have minus J times something, we call that epsilon double prime. Now epsilon prime is just epsilon relative epsilon naught. It's what we're used to. This term right here dictates dielectric losses, bound charge that's just frictionally heating. So the epsilon prime, double prime, that's the loss term. And it is a strong function of frequency. This is basically to get you introduced to this area so you have it in the back of your mind. This stuff is done because we use dielectrics. And the lower the value of epsilon double prime, the better the dielectric. That's the goal. You would like it to be 0, but it's not feasible. There always is some loss in any real dielectric. So, and it's a strong function of frequency. So then we get into this deal. Well, if that's the case, what do the equations look like? If we assume that, and this is true, if we assume we're going to say that sigma is 0, Dr. Whitmer's book doesn't, but now we're talking about just the lossy dielectric. Then I'd have curl of H equal to J omega, and here it would be epsilon prime minus J epsilon double prime times E. It's just J omega epsilon complex. Do y'all follow me? Now I'm going to go ahead and do the math on this one. So here I get what? I get J omega epsilon prime times E, but then I have J times J, which is minus 1, times the minus is plus, then I have plus omega epsilon double prime times E. Now this is the loss, this is the thing called the loss term, right there. And you see, it's just like sigma E. The omega epsilon double prime is just effectively like sigma in the equation that we had. All right, so that's curl of H. Now, how do they actually go about, when they talk about lossy dielectrics, if any of you work on any of the energy scavenging things like for cars, the batteries, where they try and scavenge the axial power by braking systems, generating things and recover it. Anytime you're doing that, you're probably dealing with capacitors that have fairly significant values and very large relative permittivities, dielectric constants. And it becomes, I'll tell you this much, this course sort of introduces you into things you need to be aware of when you go out there in the real job, because some of you will get involved in this. Trust me, all these new cars, especially autonomous vehicles, they're using everything they can to scavenge energy when they try to slow down and anything like that. Probably some of them will have energy scavenging that just uses something like a solar cell, or maybe even they just scavenge the electromagnetic signatures in cities where they can put up wideband antennas and just pull out some energy from that. But you have to be aware of this. Now, how do we go about quantifying dielectrics and stuff? Well, normally what's done is this, and this is just to get an idea, give it a figure of merit, give it a better understanding of the dielectrics you're talking about. When we have curl of H, that's the total current density, I should say. That's equal to, I'm going to assume sigma is 0 for this one too. That's equal to J omega epsilon prime times E plus omega epsilon double prime times E. Y'all follow me? So here's what's done. Usually they plot on the horizontal axis the real part of the curl of H, and that's just equal to omega epsilon double prime times E. And then on the vertical axis they plot the imaginary part of curl of H. So the imaginary part is nothing more than omega epsilon prime times E. Y'all follow me on that? Okay, what does that really do for me? Well, y'all see you can get rid of the omega and get rid of E, right? You can get rid of those in terms of the ratio of the two. And if you just think of plotting, because this is really what you're doing. When you plot this stuff, what you're really doing is you're plotting epsilon double prime versus epsilon prime. And epsilon prime is always much, much greater than epsilon double prime, or else they don't even talk about it, because then it's not even a loss, it's not a low loss dielectric, it's a high loss. And if you think of this, but I'm really showing you something that looks like this. This is in the book, where this is really a ratio of, you think about this length of this side is epsilon double prime, this length is epsilon prime. It's a ratio of epsilon double prime to epsilon prime, and this is called, that, even though it's a symbol for skin depth, is also the symbol for something we call the lost hand. Write this down. The lost hand, or lost tangent, delta, and what it means is this: if you take the tangent of that angle, it's equal to the opposite, or epsilon double prime over epsilon prime. Now remember, this is just a way of getting an idea of how good these dielectrics are. So typically, the lost tan is like 10 to the minus 4, 10 to the minus 5, which means epsilon prime is 10 to the 5th, 10 to the 4th times epsilon double prime. You all follow me on this, class? Most of the current is displacement current based on this equation right here. It would be most of the current is right there. That magnitude is much, much greater than this. Orders of magnitude. 4 orders of magnitude or more. And also, I'll say one other thing. Do you remember the tangent of a small number? Tangent of x is about x when x is small. How many remember that? All right. So normally what they just do is, because these numbers are small, they'll say this will have a value. They'll just give you the value of gamma, or gamma there, and they won't even take the tangent of it. They'll just show you that. So in the book, and I wish I had a better book, it's falling apart. But if you look in the back of his book, he has the lost at, what is that, 420 or 625? On page 625, he shows you the lost tan, that's tangent of lambda at 1 megahertz,
for air, which is 0, and then they show it for glass, which is about 0.004, and it shows you for a whole bunch of stuff. But the idea is, this is not a course in material science, but you have to be aware of this when you do engineering, and you really do, for a lot of reasons, especially heating. Because, did you have any course that taught you the difference between electrolytic and regular microcapacitors, or not? How many know, heard the term electrolytic capacitor? Can you tell me one thing about them that make them unique and dangerous? Yeah, here's the deal. You can have a DC voltage across them with a ripple, but you can never have an AC voltage. You can't drive current the opposite direction through one. In other words, you can't get any kind of full wave effect on those things. The reason is, their dielectrics are in like a gooey liquid kind of stuff, if you ever cut one open, or a paste, and they flip and they heat up a lot. I mean, they're great because you get a lot of capacitance. It's got a huge value for epsilon relative. They do have some leakage, so they're used in power supplies and things like that, but they're not used for energy storage. But if you ever put AC through them for any length of time, you'll heat them up and they'll blow up. And I have personally seen a high energy capacitor that was used for a railgun. I didn't do this, but I saw the thing, it was blown up. Somebody forgot to make sure that current couldn't. You're supposed to have critically damped or underdamped systems in terms of the current waveform that drives it. Somebody forgot that, and they let an underdamped waveform drive down the current on I think it was a railgun, but I can't say for sure. And it blew the thing up. Well, the dangerous thing is you got a grenade. When that thing goes off and heats up, it is like a stick of dynamite and a half, and it can kill you. So, just practical knowledge. Don't kill yourself. And you know, the most dangerous people are the most enthusiastic people and stuff like that. Because I had a railgun project long ago. I'll tell that story some other day. Those kids, they're shooting over a mile a second. I came down there. They take these Lexan blocks. It's what hockey rinks are made of. It's just plastic. They're counter boring them. They're putting nails in there. They're trying to get something that's a hard target penetrate. They're trying to shoot through blocks this big. I mean, leave these kids alone for an hour. Trying to get the death gun. So I'm just telling you, be careful, especially young guys. All right. So now we're going to go into conductors, good conductors, and really today my goal was to go through lossless, lossy, and then good conductors, so I can show you really the important things, the differences, and I'll try to contrast them as best I can. Okay, now, these are going to be for good conductors, or you might say very lossy media, very lossy dielectrics. Alright, now I didn't define this clearly, but here's the one thing you always do. If you take a look at curl of H, some people call that the Maxwell current density. When I was in my doctoral program, that's what they called it. It's equal to sigma E, that's actual current flowing, and it's plus really J omega epsilon, and here we're not talking about lossy dielectrics, it's a very lossy dielectrics, very lossy media. You gotta be careful about that. Plus J omega epsilon times E, okay? Now, when we have a good conductor, look, this is real current J, this is displacement current. We can call it J displacement. So, a good conductor will have a real current value much greater than the displacement current. And the way you can see that is simply take sigma. If sigma is much, much greater than omega epsilon, that is a good conductor. Are you with me on this? So that's how come if you take a look at things like copper, which has a conductivity of 5.8 times 10 to the 7th Siemens per meter, or one of them, and compare that to the value of omega epsilon for any frequency of interest, for any, this is insignificant, it's like 5, 6 orders of magnitude less, you follow me? So that's the definition of a good conductor. In your mind, what comes to mind when I say, I'd like an example of a good conductor?
Copper.
Copper probably the most common. Gold, right? Silver's a little better, not by much. And conductivity, by the way, electrical conductivity and thermal, is a strong function of temperature. I just want you to make sure you're aware of this. That things that are good conductors at room temperature may not necessarily be good conductors when you're at very high or very low temperatures. And you gotta be aware of that. But we're talking about room temperature. So, we take a look at this good conductors. First, we take a look at what the propagation constant is, which is J omega mu times sigma plus J omega epsilon. Then we're going to take a look at eta, which is square root of J omega mu over sigma plus J omega epsilon. From that, we're going to get the phase velocity, which is omega over beta. And then, after that, we'll talk about some interesting effects, especially right here. So with this one, can you all see this okay? All right, for that one particularly, when sigma is much greater than omega epsilon, which is the condition we're talking about, this is true. Well, what happens here? You can erase that, can't you? Because omega epsilon is so much less, it's added to sigma. If sigma is 1,000,000 and omega epsilon is 1,000,000, then basically it's 1,000,000. You all follow me? So what happens there? Well, what do you know about J, first of all? J, it's an imaginary number. It can be rendered as e to the J pi, right, over 2, 90 degrees. Do you agree with that? Or I could just say e to the J, 90 degrees. So what is the square root of J? Well, that would be e to the J pi over 4, or e to the J 45 degrees, right? Well, e to the J 45 degrees can be expanded using Euler's identity as cosine of 45 plus J sine of 45. What's the cosine of 45 degrees? Same as the sine. 0.707, isn't it? 1 over square root of 2. So this is really 1 over the square root of 2 times 1 plus J, if you look at it. You agree with this? I'm trying to make it simple. So I come over here, and when I look at this, what I have is square root of J is really 1 over square root of 2 times quantity 1 plus J, and then it's times the square root of omega mu sigma. You all follow me? Now this part is just to simplify things. You see how I have square root of 2 outside, 1 over square root of 2? I can take that inside and just put it as 2 there. You all follow me? Now, one other thing, what is omega in terms of F? Omega is 2 pi F, right? So if I put 2 pi F divided by 2, that's pi F, right? So what you end up getting is this. You get that gamma is equal to 1 plus J times the square root of pi F mu sigma. And it means this, since gamma is equal to alpha plus J beta, that alpha is equal to beta is equal to the square root of pi F mu sigma when you talk about a good conductor. Beta and alpha have the same exact value. You got that, everyone? Now that's important. So next we go to the intrinsic impedance. And again, the intrinsic impedance, I'm over, am I not? Well, let me just get this out of the way. That's equal to square root of J omega mu over sigma plus J omega epsilon, right? Now, when it's a good conductor, what happens here? Somebody help me out here. Ignore omega and epsilon, right? Because sigma is so much greater. You all follow me? It's added. Now, what does that become? Well, here you can write it a lot of ways. I'm not even going to blow up the J in terms of 1 plus J over square root of 2. I'm just going to say this is really square root of omega mu over sigma at an angle e to the J 45 degrees. Do y'all follow me? Only thing I've done there
I didn't even bother fussing with that, making it real and imaginary. I'm just gonna say it's omega mu over sigma at an angle of 45 degrees, which means it has a real and a complex part. Finally, the last thing I wanna cover, what's the phase velocity? Class? Phase velocity is omega, you guys will get that, over beta, but beta is what? Omega is 2 pi f, right? And beta is square root of pi f mu sigma. Y'all see this here? Now, what do you notice you can do? Well, I can take, I got square root of pi, square root of f there, I've got pi f there. What I can do is this. I can make this equal to 2 times square root of pi f over mu sigma. We'll talk more about that on Monday, but I'm going to give you some homework. Make sure you do it before the class on Monday, because a lot of this stuff is going to start, it's going to require you to have an understanding of the prior stuff. And appreciate you coming here. I'll just go ahead and send some comments up the chain so we can get it better. I asked, man, I really did. I appreciate it. Now, if you need, does anybody need to see me today? You do? I'm gonna go up to my office. My office is 423.